Yeah, we should both record. Well, good afternoon. My name is Jackie Adamson, and I'm Director of Member Services for the South Carolina Association of Licensed Trades. We're delighted to have you all today. This is one of the presentations, seminars, or webinars that we've had in a series of our technical training group for this year. We have a couple more left for the rest of the year, and I'll touch on those in a minute. First of all, let me just a little bit of housekeeping. Please feel free to stop Joey right then if you have a question. We can always learn from one another. Just, do hit the chat box, or if you want to just interrupt any way you want, we certainly want to we want this time to be well spent for you. I'm also going to talk to you just briefly that our next, and thank you, Joey, for rescheduling. I'm sorry you were ill, but we appreciate you willing to do it again. On the 20th, our next technical training webinar will be on zoning system, operation and diagnostics. And on the 26th of October, we have how to teach a technician to sell, customer connection. We're excited about that. We've had a lot of requests for that. November 2nd, you all see us talking about Service Nation, Service Roundtable rebates. And then you'll say to me, well, I don't know how to get that money, and it's too much trouble, I'm sure. But what we're going to do is we're going to show you how to do it. And I'm going to recommend that you have your accounting people participate as well, and maybe even your office managers, if you like. November 17th will be our last technical training webinar, and that's going to be on heat pump heating. So with that, I'm going to take a moment and introduce our speaker today. Joey, I'm going to introduce you. How am I going to do that? I just had it up, and then when I gave you the count, I messed up. So here we go. All right. Joey Henderson, if you participated in our presentations before, you know Joey. He is I'm sorry, y'all, I apologize this. He's with HVAC Consulting Service. He has a total of 30 years. Should we say 31 now, maybe, Joey? In HVAC, 25 years as an instructor, 15 as a technical representative, 20 as an HVAC contractor. He's also a member of our board of directors and been involved with SCONT for 25 years. And we are delighted to have him. For any of you who need NATE or BPI CE for this, you would need to have actually been registered individually for that. So I just want to share that with you. And with that, I'm going to turn it over to Joey and not taking more of his time. Thank you again for participating. Please ask questions. Please do.
Yes. Thanks, Jackie. If any of you have any trouble hearing me or seeing me while I'm going on, just be sure to either press your space bar. That will temporarily unmute you. Hold your space bar down and speak, and then you can just let go of your space bar. That'll put you back on mute. That way we won't get any feedback. And like Jackie said, if you got a question while I'm discussing, feel free to just jump in or throw your little comment up, or however you need to do it. If you have questions that you'd like to email out later, please do, and I'll get a hold of those and answer them for you. And also just to let you know that what we're going to do is concentrate on measuring static pressure, and more importantly, taking those readings and how to correctly diagnose airflow problems. I was some of y'all know this, but I was a tech rep for Carrier and then for Train for a little over 15 years. And a lot of my troubleshooting on job sites was airflow problems. So we will discuss that. This is not a full-blown air duct design class, although I can do that. Airflow is my love. Duct design is my love. And if you guys want something like that, it's roughly about a 2-hour class at best. Sometimes longer if we wanted to, but 2 hours is about all we can do on a Zoom, I think. But it'd be good and thorough. If you would be interested in that, please let Jackie know, along with our other classes we got going on. So without further ado, let me bring up the presentation and then share it with you guys. And again, if you have any trouble seeing it or hearing me, just say so. And here we go. Okay. So airflow measurement and diagnostics, I'm going to keep this simple and straightforward, try to cut through all the jargon that you hear a lot in technical manuals and just try to take it to boots on the ground is the way I put it, so you can actually use it. When I'm going through this, if you think of problems you've been having out in the field or concerns and you go, oh yeah, and a red light comes on or something, just holler, because that's what this is all about. So the first thing I want to talk about is what is static pressure in the ductwork. I think we're all knowing that air flows through the ductwork, and this is an example, and it's just an illustration. It's not necessarily excuse me. It is not necessarily a direct depiction of what goes on in the duct, but it gives you an idea. So if you look up top here, here's how the air comes in. It's return air. It gets pulled into the grill. And as we know, it gets pulled in through the ductwork. But as it travels through the ductwork, this air takes a lot of turns. Now, the one thing that this illustration doesn't really show well, I want to point out is when air comes around a sharp turn like this, it does not turn smoothly as it shows. It's actually quite turbulent, especially right there in these corners. If you can think about in a car, if you were flying down the inside track here and you had to hang a hard left, you'd do nothing but crash into everybody else. But if you're on the outside track and you're coming around, you have a lot easier turn to make. So air does naturally turn very smoothly on the outside turns, but not on the inside. Excuse me. And that will come into play later on as we look at air duct design issues concerning inside turns versus outside turns on ductwork. But as that air comes through here, there's a lot of resistance to that airflow. And that air, as it flows through, drags along the outside edges of the pipe. And that causes resistance to flow. The internal arrows here, they represent what's called velocity. And that's the speed of the air moving through the duct. We're not going to talk too much about that, although it is very important in duct design, and that could be on a later class. But as we come through here and we come around the corner into the blower motor, that is our return air. So there's resistance as we take turns and come down lengths of pipe. So the longer the pipe, of course, the greater the resistance of flow that blower motor's got to pull through. As the blower motor pulls through here, it pushes air back through, and this is the supply duct. So we got the return air, and then we got the supply air. Each have their own static pressure changes, and you don't ever want to read these together as one number. That's very tempting to do, to put a meter on one end and a meter on the other, and our hoses, and then just read one number and say, ta-da, I got the perfect total static. We don't want to do that. We want the total to be in good shape. We want the return to be in good shape as well. So I'm gonna give you an example of that right here. This right here, I know some of you may or may not recognize this picture of here. It's an old incline manometer. And that incline manometer right there is showing you a total of air coming in and air sucking in and air pushing in. And these are just really two different pressures, not necessarily a negative and a positive, in the sense that you would take this 0.35 inches of static right here and subtract 0.15. That's not how that works. The plus simply means that this side goes into the positive side of the duct system. The minus here simply means you're reading the return side of the duct system. And the way they've got this drawn is they're taking the static pressure right here in the blower housing. That way you're measuring the resistance of this air filter as well. I got another picture, I think, that will depict this even better. And then they're showing the supply here before this A coil. So if this is a gas furnace, which in this case it is, anybody wants to know, how do you take the static pressure of the supply air before the A coil? Well, what you can do, it's a little trick, is you take out the high limit switch and put your static pressure probe right there where the high limit switch goes. That way you're getting air flow through the heat exchanger right before it exits and right before it hits that A coil. And that will give you a good reading. Just a note, don't turn on the furnace, only the blower. Okay. All right. So here we go. We're going through there. Air flows through the supply side, and the static pressure is shown by these little arrows as the air pushes against the outside of the pipes and as they're going up through here as well. So static pressure is the resistance of airflow through the ductwork. We have return static, and then we have supply static, okay? The total of these two is called external static pressure. Anything that's external from the equipment that it was rated for. So for instance, a gas furnace, they don't have any rating for the A coil or for the filter. You have to add that in to your static pressure reading. An air handler for a heat pump is different because the evaporator coil is already installed in the inside the air handler prior to you buying it. The manufacturer designed the blower to overcome the pressure drop through the evaporator coil in the factory. But a gas furnace, being that it has multiple evaporator coils that you can put on it, you have to add the pressure drop of that evaporator coil once it's installed and when you're taking readings. These total numbers here is a total of 0.5 inches of static, a total of 0.5 inches of static. You take that 0.35 and you're going to add this 0.15 for a total of 0.5 inches of static. But notice the static pressure on the supply side is higher than the return side, and you want that balance. You always want the supply side static pressure higher than the low side static pressure. You don't want them dead even because you want the return side to be lower pressure, slower air, and quieter. The supply side, you want a little bit more static pressure so you can speed that air up and get it to throw out of the vents, okay? So that's why you really don't want to see just a total reading on 1 meter. You want to see them individual and then see where your return static compares to your supply static. So return static should be lower than the supply. We'll get into a slide here in a minute and talk about what our totals should be depending on the type of blower motor you got. Now that you kind of got an idea of what static pressure is, how do you measure static pressure? Well, we got a few instruments that we can measure it. This over here, this magnetic, was a tried and true way to measure. And it used to be the only way to measure outside of water. And it was good, but you had to keep it level and you had to make sure you had it calibrated correctly. But then we got into the digital world, and very common now are dual port manometers. And that's what these are, manometers. And they measure inches of water column. Now, to give you an idea of the pressure of inches of water column, there's roughly 28 inches of water column pressure within 1 PSI. So for instance, if you had a column of water, okay, and it was halfway up that column and you had it 0, and then you put a mark 1 inch higher from where the water sits, and you put pressure, air pressure on that tube, it would take, well, let's put it this way. If you got a 30 inches on that column and your water sitting at the bottom, 1 pound of pressure would raise that water 28 inches up on that column. So 1 pound of pressure would move water 28 inches up vertically. Well, we're not looking at 1 pound of pressure. We're looking at 0.35 to 0.5 inches of water column. So not even 1 inch of water column out of that whole 28. That's why we can't use a regular gauge. So we're really measuring very, very small amounts of pressure here. So we need to measure in inches of water column. These digital gauges do a good job, okay? And typically you can get little meters like this, but there's an important fact here is you got to know what to use to measure correctly. This is a kit I've often used. Field Piece has got great kits. iConnect. Everybody now has got little kits out there, but make sure that you get the tubing and you get these static tips over here on the left. We're going to talk about that here in a minute. These static tip pressures are critical to measuring correct airflow. What these are if you look right here at the end, that is a closed tip. It's like a bullet, okay? And over here on the side are your air holes. So right here are the air holes that we're looking at. So what happens as you've got that static pressure tip pointed into the airstream, the air hits that tip and it flows around it. As you can see that drawing I got there, as it flows around it, the air drags along the outside edges of this static pressure tip, and it's now only reading static pressure that's pushing against that tube, not velocity pressure. If we had a hole at the end of this tube, it would be velocity pressure and static pressure together to give you total CFM. We're not looking at that. We're only looking at static pressure. So hence, this is not a pitot tube. I've had a lot of people who've kind of done airflow measurements or heard about it. They mistakenly call this a pitot tube, but it is not a pitot tube. This is a static pressure tip only. And that's really all you need if you're just going to measure static pressure. Now, if you've got a manometer that takes velocity pressure and static pressure and uses the dimensions of the duct to give you CFM, then more power to you, but we kind of got a little bit easier way these days to do that. So where's the best place to take it? As you saw in the other drawing, we were taking the return and the supply on that furnace. Here's a depiction of an air handler. And the best place to take it is after everything in the return duct, including your filter, but before anything the manufacturer has installed in the system. So here, this is an air handler. The evaporator coil was pre-installed by the manufacturer. So they have sized the horsepower of this blower to take into account this coil. Usually not a dirty coil, not even a wet coil. We're not going to get too deep into that today, but when you get this loaded up with humidity, with moisture, condensation, it does change the resistance against that blower. Not a whole lot, but some. Also over here on the supply side, strip heaters also are not added into the blower because you can have different size strip heaters, and they do add a little resistance between a wet evaporated coil and maybe higher heat strips. You might change your static pressure reading off by 0.1, 0.05, something like that. Not a great deal, but a little bit. Your filters, as many of you may know, are a tremendous change in static pressure. I've had my only airflow issue is the customer went and bought some $30 Wabba Jabba high thick filter that would catch, everything down to dust mites. And of course, it also catches airflow, and it is a big problem. Unless you have a duct return system that was designed to handle a very heavy pressure drop filter, you can't use them. They will cause terrible issues. Now, the way you can check it, pretty simple. Pull out the filter, run the unit, and measure the static pressure on the return side, right there. Then put a filter back in, close it up, turn it back on, read it again. Whatever the pressure drop is between with the filter, without it, now you know. And add that in. If your blower is a constant CFM, which we'll talk about, it'll ramp up to overcome it. But remember, the more a variable speed motor, i.e. constant CFM, has to ramp up, the more money it costs to run it, and the efficiency goes out the window. Performance is still there up to a limit, even for a variable speed, but efficiency is gone. You got to remember, these variable speed motors are meant to run at a certain RPMs for efficiency, just like cars. So if you've got to put the pedal to the metal to get out of the driveway, you can forget getting the miles per gallon on that windshield. Same thing with a variable speed motor. If it's got to ramp up like a hurricane just to start up and run, you can forget getting any kind of efficiency out of that motor. I think some of you guys have dealt with that. That sounds like poltergeist in a bonus room because all the grills are rattling. That's because the variable speed's ramped up like a hurricane. So back to the static pressure reading here. Got a little tangent there. Return, static. Measure them separately, record them separately, and then look at them. If your static pressure, We're going into some troubleshooting here. If your static pressure is all on the return, let's say you got a total of 0.5 and you're going, all right, I got a total of 0.5 inches of static. But if 0.4 of it is on the return, you're in trouble. You're in big trouble. You don't want all your static backed up on the return side. That means you got either a return box, flex duct, combination of both, too small a return grill. Somewhere you've got too high return static. Remember, you want that static lower than the supply static. Now, if you look at that, you'll find that, let's say you go to 0.5 and you've got a regular PSC motor in there and you got 0.4 on the return, you're going to find out that you ain't going to get more than about 0.1, 0.15 on the supply because there's no air left. There's no air left to get to the supply system. You got it all dammed up in the return and the motor can't pull it out of that return because it's so restrictive. So get the return static down and guess what? You'll get the supply static up because now you're going to be able to move more air into the supply duct and get it to condition the house. Next, how about blower motors? They also affect static pressure and they are rated at certain static pressure readings. Not all blower motors are equal. Not all ECM motors are equal. If you went to my ECM class, you'd understand that. Let's look at PSC motors. PSC motors, which are slowly going out, okay? So we all know the X13 is becoming the dominant motor for most about everybody's average unit these days. We'll talk about that in a minute. There's still a lot of PSC motors out there. Majority of them are not running. Majority of them are not running at full capacity at all. This is not just me talking. This is a study that's been going on since, oh my gosh, I think the Department of Energy started doing studies in the late 70s, early 80s, and they continue to find out that nobody's getting the efficiency because of airflow, hence the SEER 2 standard that's coming out. It's all due to airflow, and I'm glad for that. We need more realistic airflow in our SEER ratings, and we're going to hopefully get it. PSC motor. PSC motors mostly, but not always, but mostly in all of your residential equipment are designed to give you the most airflow they can deliver at a total of 0.5 inches of static. Okay, that's external from the equipment. So everything in that ductwork can't add up to more than 0.5. Now we're still not talking about, we're talking about getting balanced. So if you got a PSC motor, you don't want it to be running, 0.4 on the return. You want to be more like 0.15 on the return and about 0.2 on the supply. You don't ever want to start up a brand new unit at its maximum static pressure. Think about it. If you do that, you have no room for dirt on the coils. You have no room for the filters to get dirty. The best you'll ever have is brand new. After that, it's just going to go downhill. So again, it's like a car. You don't want to have to use all the horsepower of a car to get it out of the driveway. You ain't got no room to go up a hill with it. Okay. Kind of like my old 4-cylinder Ranger I had. As soon as you put a block of wood, a wood back there and went uphill, forget it. You're not going nowhere. I got no horsepower. PSC motors are the same way. So when you're measuring for PSC motors, yes, they can handle up to a 0.5, no more. Now, if you read a static pressure of say 0.7 on a PSC motor, it's not delivering the airflow. You're not getting the tonnage of airflow you think you're getting. Okay. Most PSC motors, if you look at the blower tables, they tap out at about 0.35, 0.4. 0.5 is the max you'll ever see on a regular PSC motor, but it's not guaranteed. Some of the lower, hate to say it, but working from the manufacturer side, sometimes the way they lower the cost of an air handler or a furnace is they put a small horsepower motor in there and they'll rate that CFM at a 0.3, 0.35 inches of static total. That's hard to achieve on a standard duct system. Okay. We'll look at that when we do duct design. We'll look more at blower tables. Now, notice I got a note here. That total of 0.5 includes X13 motors. Okay. So let's talk about that next. X13 motors. That's just the brand name for the constant torque ECM motors, okay? ECM motors, X13s, are not variable speed. They are not a constant CFM motor. They do not work the same way at all, okay? A constant torque motor, what it does is that when it starts getting close to its limit of 0.5, maybe 0.6, a little bit more than the PSC, it's not going to lose its CFM capacity as quickly, okay? A PSC motor, once it reaches its peak static pressure of 0.5, it's delivering airflow. As soon as it gets past that threshold of 0.5, the airflow starts dropping like a nosedive. All right, we're crashing and burning, baby, at 0.6, 0.65, 0.7. It's over. Coils will start freezing up. It's bad. All right, but you're not getting all the airflow you need. At a constant torque, you hit the same threshold that a PSC motor hits, and it holds the nose up a lot longer, and it's a slow descent on airflow. So at 0.6, it's hanging in there. 0.7, it's dropping some more, and about a 0.8, it's gone. Okay, so it's got a little bit more torque, and it holds its own. The commonality between ECM motor X13 and a constant CFM motor versus a constant torque X13 is they both have that programmable module on the back side of that motor. The motors themselves are the same. They are a three-phase DC wound motor. So they're high efficient. That's why they use them. But they don't do the same job as a constant CFM. Speaking of constant CFM, here we go. A constant CFM motor, which in the old days was always referred to as a variable speed motor, can handle up to, depending on the manufacturer, depending on the size of the equipment, to a 0.8 1-inch total static. It's a beast. It's a huge motor, horsepower wise, and they tap into it with the program. But understand, it is not variable air flow, or air volume, I should say. That's why they change it from variable speed to constant CFM. One, to not get it confused with the constant torque X13. But secondly, most people, in their minds, they thought, well, we're getting variable airflow through the duct system with a variable speed. No, you're not. You're getting variable velocity because it ramps up the RPMs to overcome static pressure. Let me give you an example. You got a car, you put it in cruise, and you're cruising down the road and you're going, say, 70 miles an hour. Well, when you go uphill, does the car speed up when it goes uphill? It does not. It increases the RPMs of the engine to maintain that constant speed, okay? So when we put the cruise control in the car, we're trying to maintain speed. Consequently, on a variable speed motor, a constant CFM motor, you program in, let me choose a number, 800 CFMs for this unit. So what it does is as it reads the resistance in the duct system, it increases RPMs to maintain CFM. It increases or decreases RPMs to maintain that constant CFM. So that's what you're hearing. If as a filter gets dirty or the evaporator coil gets dirty, that constant CFM motor will increase its RPMs. Therefore, there's the variable speed aspect of it to maintain whatever CFM you've got it set for from the beginning, okay? That's where the noise comes in. That's why it gets noisier, because it's having to ramp up to overcome the static pressure. Now, just real quick, the way it knows static pressure is it looks at, they program this from the factory, by the way, but they do a reading and they measure that at each static point, 0.1, 0.2, 0.3, they measure how much current the motor needs to maintain CFM at those increasing static pressures. They program that in. So that module in the back of that ECM motor is looking at the current draw compared to the voltage coming in And with that, the program says, okay, we got to speed the motor up an X amount of RPMs to maintain CFM. Hope that helps. But again, just like any other motor, you don't want to start it off ramped up to maximum horsepower just to get going. That's like having a ginormous truck with a V8 engine in it and a 350 motor in there. And in order to even get out of your flat driveway, you got to push that baby down to the floor. That's not good, right? You want that available horsepower when you load up the truck, when you got to pull something, when you got to go uphill with a load. Same thing. We want that constant CFM motor to start off at a very mild static, okay? So that when it begins to load up due to dirty filters, dirty coils, it's got the horsepower to get there. And then when the coils get cleaned, when the filter gets changed, it comes back down to its normal level. Just like when you get up that hill and you get to another flat way, the engine settles down and back to good gas mileage on the highway again. Same thing with that motor. So, non-constant CFM motors, okay, we want operating static around a total of 0.3. So about a 0.1 on the return, about a 0.2 on the supply. This is not where you put your ductulators. Don't go there, okay? That's a whole other design problem. But I'm just talking about when you start that bad boy up and you're reading static pressure, ideally, the best you could really hope for is a 0.1 on the return and a 0.2 on the supply. That's operating static. Okay, why? Because now you got room for dirty coils and filters down the road. And then you come back to a good reading. Now, let's say you got a job you're going up to, or you've installed it, and the battery went dead in the manometer, or you're like, oh, shoot, I don't have a manometer with me. All right. If it's a PSC motor, if it's moving the full amount of airflow it's supposed to move, pull the amp draw on the motor, okay? Close the doors up, run the fan motor in constant airflow, fan on. Make sure it's set for medium or high airflow. Check your amperage at your disconnect with the unit all closed up. It should be moving as close as rated amps as possible. That means it's moving that full airflow that it's designed for. If it's pulling less amps, PSC motor pulling less amps than it's rated for, it's moving less air. It's restricted. A PSC motor does not have the ability to ramp up horsepower to overcome static. Therefore, it chokes it. So a PSC motor, you go up to it, you pull amp draw on that PSC motor. If it's pulling less amps than rated, it's moving less air. It's a direct correlation. If it's maximum amps, then it's moving maximum air and you're in good shape. That's another quick way to check. What you don't know, even if it's moving max air across that coil, you still don't know whether you got a high return static or not. But you do know you're getting capacity out of the unit, and that's a good thing. Now let's look at constant torque. Okay, sorry. So total ESP, no more than 0.3, starting out PSC motors. Constant CFM motors, by the way, that was true for an X13 as well, right? X13's got a little bit more leeway. So if you're at a 0.3 to 0.35, that's fine. Now let's look at a constant CFM system. This is a true variable speed motor. Remember, it's a big dog. It can handle all the way up to 1 inch of static, all the way up to 1 inch of static. But you don't want to start off there. You don't want to push it to that from the beginning. Start it off around a 0.35 to 0.5 total. So now you can do a 0.15 on the supply, on the return, and a 0.2 on the supply. Total about a 0.35, all the way up to about a 1/2 inch total. What that's going to do is now you're going to be pulling about half its rated amps, roughly, okay? And it's going to be running at a very steady RPMs. It'll be quiet, it'll be efficient, and it'll be ready to handle the load of a dirty filter or dirty coil or both when needed. And then once those get cleaned and changed out, it'll come back down to its normal operating pressure. You start running a variable speed motor at higher than 0.6 total, 0.5 total, it starts ramping up. It will deliver the CFM up to about 0.8 to 1 inch of static. Your unit will get the capacity that it's rated for, okay? But it's going to do it at a cost of noise and a cost of money. There's been many jobs that I had to go out to, full tear outs, full duct system tear out, full change out, go back in. They went back in with short plenum boxes, flex supply lines, put in a wobble jobber variable speed system. It's ramped up like a hurricane, sucking water off the evaporator coil, not draining, all kinds of problems, all because it's had to ramp up from day one. And the customer is having to pay a lot of money for utility bills, and they're having water issues, and they're having airflow issues, hot and cold. You guys get the picture. I know I'm preaching to the choir probably in a lot of these cases. But if you're concerned, if you don't, static pressure isn't always a good reading. If the duct system has got boxes on it, you can take static pressure readings and throw them in the tank. If you don't have good straight airflow going through that duct system, if you got plenum boxes on there, the air is too turbulent. It's just spinning all around in that air in that box, and you're going to be reading dead airflow. You can have it's like trying to run water to that little box and take it's got little eddies all inside of it. So if you got a system, it's jammed into a tight duct system, measure the amp draw. If your constant CFM motor, your variable speed motor is pulling close to max rated amps, it is jammed up. It's either on the return of supply and it's just ramped up, trying to do all it can do to do the job because it's restricted. Got to get that airflow back, got to get that static pressure back down. All right, so keeps it quiet, keeps it efficient, and they're not paying all that extra money. And if you got it all ramped up, you can kiss the SEER rating goodbye, especially now they're doing SEER 2. So variable speed motors, operating static, 0.35 to 0.5. Mark it down, 0.35 to 0.5 total. But remember, still measure the return versus the supply. Return lower than supply, total 0.35 to 0.5. So key points, keep the external static pressure down. How do we do that? Keep your trunk lines, return and supply, as straight as you possibly can. I tore out, I installed personally hundreds of duct systems. When I sold jobs, it was a full tear out 8 out of 10 times. Yes, I was the most expensive guy on the block usually. And yes, it took more time to do the job. So while some guys were slamming in 3 a day, I was doing not that many. But when we got done, everybody was happy. I had no callbacks. I've never lost a compressor, not one. I've never lost a compressor. I never lost a replacement compressor after we fixed the ductwork. Airflow is king. So keep the static pressure down. Think about a tree, straight trunks as much as possible. If you have to do a trunk line, and I mean a plenum box, then please use squared rounds and round Ys. We'll talk about that in a minute. So take a look at this drawing. Okay. How are we doing? Good, 20 minutes. In this drawing right here, it's a good little depiction. Okay. Here's a return coming down. And look at this right here. This is a really good illustration of what air does inside that duct. When it takes that super tight corner right there, a lot of turbulence starts to build up. Now, what turbulence causes is 2 things: a loss of energy in the air, so you're losing the velocity. It also creates a tremendous amount of drag for the motor to pull against. As we get to the outer edge here, air builds up in this pocket right here and creates really a nice curve. So let me give you a little understanding here is that if a lot of you guys might build your own ductwork still in the shop, rectangular ductwork at that, the outside turn really counts for very little on helping the airflow. It does its own. The dynamics of flow through this box right here, through this hard 90 elbow, it does its own curve by itself. Trust me, adding an outside miter turn does very little for airflow. A little, but not as much as you'd think. The inside is huge. This is where all the drag is, right here on the inside turn. If you miter the inside and leave the outside alone, you'll cut the pressure drop through this elbow almost in half. It is a massive difference. So when you do a return box next to an air handle, you got your air handle on the floor and you got your return box coming into the side of it. If you will do a miter turn on the inside and then square it off on the outside to sit on the floor, it'll make all the difference in the world. Now, if you've got a commercial job and you're putting turning vanes in here, well, that's a whole different story. Residentially, we're not doing turning vanes, and that's what we're talking about. So residentially, you want to put an inside turned elbow if you have to do a box at all. Me personally, if I can get a squared around with a round elbow, 1,000,000 times over this is even better, okay? Squared around with a round elbow is about 15 to 25 foot of equivalent length. This bad boy right here, depending on how close it is to the unit, can be as much as 125 foot of equivalent length. The pressure drop is huge compared to squared around and a round elbow, okay? I'm a big, if I had a van and drove around with a big sign, I'd say squared arounds, round wides, round elbows. That'd be my motto, okay? So come here through the unit. Now you think about all this air is coming through. It's getting rushed into this unit and it's getting sucked into a vortex, okay? Air is just getting pulled into it, going through a washing machine, okay? When it comes out of that air handler, buddy, it is turbulent. Think of a waterfall. It's coming out of a waterfall, hits the bottom. That water is turning all over the place. All the energy is in that turbulent water. Air is a fluid. It's coming out of there very turbulent. Now, as it comes out of here, kind of comes out in this little small little bubble here. And as it travels through the duct, it begins to expand through the ductwork. As it expands, it begins to straighten out. Just like when you look and see a water coming down off a waterfall, as it flows down that river, what does it do? It begins to straighten back out, take a smooth turn. If you got rocks and you got an immediate turn after waterfall, what does the water do? You'll see it. It just starts doing these little dead air pockets, these little eddies, all right? As it swerves around, twists and turns, you get these little dead pockets of water just sitting there, just going nowhere. Air does the exact same thing. So when the air comes out of a unit, you have got to give it an opportunity to straighten back out before you do anything else to it, okay? So here, we've got a distance before we do anything else, okay? A round Y splits the air so much better than a box. So let me give you a visual. I'm going to build this one day, I promise. Let me give you a visual. Let's take, you've got a little putt-putt course, okay? And I got the rails going down to the end. And at the end of it is just a T, just a T. So we got a flat T turn. So you go down the course and you can go left or you can go right. There's no Y splitter. Now you take a big 55-gallon drum of golf balls and you pour them out down that course and they'll flow straight down. But the minute they hit that wall, are they going to evenly turn left and evenly turn right? Heck no. Majority of them are going to do what? Hit that wall and come straight back. You're going to have a collision of golf balls. Now, some will go left, some will go right, but the majority, and let's just think, I was just constantly shooting these golf balls, just recirculating them back through it. What do you think they're going to do? Majority of them are going to stay right there in that little intersection. And eventually, through enough pressure, you're going to push more left, push more right. How many? Who knows? All right. Now, let's look at the other way. Let's come down the same course, but then add the little splitter. You know, the little V-shaped splitter. Now you throw all your golf balls. What's going to happen? Whoosh. They go left and they go right. No resistance, no problem. Smooth change. That's why you don't want to use bullhead T plenums. if I can encourage you, please, please, please don't use them anymore. All right. Return is no different. Return is no different. You want to swoop in with the return and swoop out with the supply. If I had a short job where my unit was in between two short spaces and I had to go left and right with my trunk lines, a squared around and a round Y is 2 feet long, 2 feet. And I could get a squared around and a round Y on the supply and the returns and then run my trunk lines left and right. Huge difference in my pressure drop. Your biggest pressure drop is at the blower. It gets less and less as it goes down line. Okay. Your blower is your biggest pressure drop. So use squared arounds and round Ys everywhere. Get rid of your bullhead tees, please. Now, when could a bullhead tee be okay to use? Well, here's the rule. Here's the rule. You really don't want a single takeoff, a single turn in the ductwork, a single fitting for 3 to 5 feet before and after the unit. Now there's a calculation for this in manual D, okay? So many feet for so much diameter of duct in order to keep it smooth air. I'll give you a new party word. It's called laminar airflow, like laminate, laminar airflow. That means straight air. You got to get the air straightened out before it makes another turn, just like water coming off the waterfall. It's got to get straightened out before it starts taking a smooth turn again. If you got an abrupt turn right after the waterfall, what's the water going to do? Swirl, turn, create eddies. Same thing in ductwork, same thing. So you know those supplies that are like 6 inches off the darn air handler. Do you get air through them? No, the air just goes shoo, straight through them, all right? Now, if you start adding scoops to make up like Band-Aids, well, scoops, yeah, they'll grab air and throw it, but they'll also cause a tremendous amount of turbulence. And some scoops create a negative pull in supply duct. I was on a job and I've seen videos of this. I ought to take a video of and show it. But you know, you got a supply register hooked to a duct that's got a scoop on the end of it inside the main duct. And I took out the very expensive, high professional, handy dandy tissue paper, okay? Put it up against the supply grill. You know what it does? Blows off, sucks back in. Blows off, sucks back in. Because of the turbulence, it's just swirling through there. So try to stay away from scoops. 3 to 5 feet. So where does the 5 feet come in? If it's a 5-ton duct system, 5-ton unit, you need 5 feet on the return and on the supply of straight duct before you do anything else. I know you can't always achieve it. I understand that. But the closer you can, the better. But the closer you pull those fittings into that air handler, the more turbulence, the higher the static pressure, and eventually the blower motor, it's just deadheaded. Okay, it's doing all it can do to pull in and push out against very short fittings. So, and I trust me, if you follow these rules, whatever duct sizing you're doing, it'll make a huge difference. Now, here's a good example of a straight trunk line with very nice straight tight flex. This has got a bullhead tee, so I poo-pooed this little drawing for that. All right. So let's just add 5 feet here in your imagination. Okay. All right. And you'll be in good shape. But here's what you usually see, right? That's the type of duct system you usually see. This came out of manual D, by the way. This is showing a small run of ducts, 3 foot, 4 foot, 5 foot. Okay. Maybe that's 6 foot. That's all that's showing. This is not your residential duct system you want to do. Okay. Don't do that. That's what kills them, right? So here's what you want to do. You want to go back to a straight trunk line. All right. Don't do that. Now take a look at this job. Here's a nice, beautiful, straight piece of flex. That's about all I can say nice about this job. This is about 4 pieces of flex being squished in around on a plenum system. By the way, this is a 5-ton duct system. As you can imagine, airflow was very pitiful. This was a job of about a $500,000 home with the highest tier AC system stuck in there on the lowest tier duct design you could ever imagine. Okay. How about this one? This is a real job. No, I didn't take it, But we all know that's not going to work. I do hope we know it's not going to work, but somebody thought it would. This is nice. Straight trunk line, looks like a giant stick bug, all right? Up high, we got our runs coming off nice and smooth. That's a good job, okay? Let's look at some do's and don'ts of our duct system install for our flex lines, okay? First of all, avoid bringing in your flex line without a hard elbow. What happens is that flex line gets bent over. We've seen it all the time. Not only are you smashing the flex, but you're creating a tremendous amount of ripples with that wire. So anytime you go down, you go across and you go down into the ceiling, use a hard elbow. Anytime you go into the house and up into the floor, use a hard elbow, because the minute you take that flex and you kink it up there to connect it to the boot, I know, been there, it will cause a restriction, and it's accumulative. So every job, once I started, my brain got expanded to the proper airflow design. I started fixing issues. Every boot has a hard elbow, period. Not every takeoff, as long as your takeoff is lined up with the boot, or maybe a slight degree off, okay. But the minute you got to do 45 or harder on a takeoff, put a hard elbow in there and let the hard elbow do the turn. Flex duct needs to be, as this picture shows right here, straight and tight as possible. And that doesn't mean just the outside jacket. Grab inside there and get that liner and pull it straight and tight. When they do flex duct airflow measurements, they put it on a machine and they grab that inside vinyl and they pull it as tight as a banjo string. And we know that doesn't happen out in the field. We know it's not realistic to expect every single piece of flex to be straight and tight. So what you want to do is reach in there, pull as tight as you can. I'd hook it up on one end and try to pull it off when I got to the other side, okay? Secondly, flex duct inherently is turbulent. The bigger you get on flex duct, the more turbulent it is compared to its metal counterpart. So without duct design, I could prove this to you, okay? But on your flex ductulators versus your metal ductulators, you will find that the bigger you get, like say a 14-inch flex, a 14-inch flex pulled straight and tight with a machine will not give you the same airflow as 14-inch pipe, because the ripples, those big rings, create valleys. And even if it's straight and tight, you still got the valleys. So the airflow is less on a flex duct. If you follow this rule of thumb, I promise you, it will correct a lot of issues with flex duct. Straight and tight, hard metal elbows for turns, and go up one size. So if you, and I got rid of almost 6-inch flex. I went to 8-inch flex for just supply runs, unless it was a bathroom. Because not every run's straight and tight. It just can't happen all the time. So this will take 4 of those turns and twists you got to make, a little bit of sag here and there. Not the Chinese water dragon, but a little bit of sag. I understand that, all right? But if you go to 8-inch flex for your runs, if you're going to run runs, if you got a 14-inch return and you want to divide that off, okay? Don't go 14-inch hard pipe to 2 12-inch flexes. It's not equivalent. I know in your mind, you're thinking you're going from 14-inch hard pipe to 2 12-inch hard pipes. It's not that way. You're really going to 2 10-inch hard pipes equivalent if you go back to 12-inch flex. If you're going to split a hard pipe to flex, use the same size flex as the hard pipe for the split. For instance, if you're going to bring in 2 returns to a 14-inch hard pipe, then bring in 2 14-inch flex returns and bring them into that 14-inch hard pipe return. Now you've pretty much evenly split the air, and you'll keep it low and slow, and you'll keep your static pressure down, okay? Hope that helps. And that's kind of basically what all this picture is saying right here. By the way, none of this is theory. I've done it, I've tested, I've done before, I've done afters. It works. I've had companies call me, said it killed a lot of their callbacks by just following these simple rules without even getting too deep into ductulators or anything like that. So hard elbows with flex turns, round Ys, no T fittings, no boxes with flex octopus, straight and tight flex runs, and upsize of flex to match the hard pipe equivalent. Okay. Now, not to go too deep into this. Let's see. Ooh, okay. Run short. This is giving you the equivalent length of duct fittings. What they did is they took the pressure drop and equated it to how many feet of duct it would be like. So for instance, let me see if I can, there we go. So here's a boot, just a straight boot. And it's sort of like a squared around, close enough for our learning purposes here. It's equivalent to 5 feet of straight duct. So the resistance of airflow through 5 feet of duct is equivalent to that boot. And that boot, by the way, is about 12 inches long, maybe shorter than that. Now, you ever use a torpedo boot to get out of a jam? Well, take a look at that bad boy. When the air's got to go through here and then up and out in such a short amount of space, that one boot is equivalent to the resistance of air flowing through 50 feet of pipe. One boot. Try to stay away from these hard fitting boots right here. If there's any other way you can do it, relocate the vent somewhere, something. These are convenient, but they are horrible for airflow. So I like to do squared arounds, pretty much like a boot, and round Ys. And look up here to round Y. A round Y is equivalent to 10 feet. Now all these, by the way, all these resistance fittings up here, they show you a little picture, but remember, it's based off of that straight air. The closer we get to that ductwork, the higher the resistance of that fitting is, or straighter we get to the blower, closer we get to the blower. But take a look at this right here. Look at this return, okay? It's worth 65 feet, just the elbow itself. If you mitered that inside turn, you'd drop that in half or more, okay? Your takeoffs, your flat takeoffs from your main trunk, your rats are worth 35 feet apiece. If you use an angle takeoff rather than a flat takeoff, it cuts it down to about 10 feet. So these are just examples of how fittings can greatly reduce your static pressure if you go to some low loss fittings. And we got one question that came through here. 4 minutes, gotcha. Okay, almost done. Hang in there. All right, next. I think I'm just about done, y'all. Don't do that. Don't do that. That flex is a little bit better on the right side there. This is the biggie right here. Which is better? This one. Your inside turn and your Y fitting. If you use turning vanes, but we don't, bad. A little better because the inside turn, the best right here. Self-explanatory. And same thing. Remember, dampers add restrictions. Cut out the scoops. If you got to have a damper in there, which I know they do for airflow measure balancing, but get rid of the scoop. Don't use a scoop. If you can, use an angle takeoff. Here's what I found for round duct. There's someone better out there, but that's the best I can find. Here's your typical rat. Just remember, it's 35 foot of restriction. And last but not least, please cut the hole to fit the round. That's been a problem I've seen. We got 6-inch or 8-inch runs with no airflow. Take them off of the trunk line. This is what you got, little 4-inch hole. Watch out for that. Do a nice hole cut. Any questions? Only 2 minutes over, not bad. Any questions? Jackie, back to you.
Hey, hold tight for just a second, Joey. We've got a question.
Okie doke.
Yeah, I'll go ask, is the static pressure, is the static pressure the reason why the modules keep going out on the X13?
I can answer that for you. Go ahead and mute your mic.
Mute the mic.
We got it. Go ahead. Oh, mute the mic. Okay, sorry.
Yeah. Okay, there we go. So a couple of reasons for X13 failures. There was at one time, not now, but everybody thinks it's forever. There was a bad set of modules that went out across the range of all manufacturers for X13s. And they did have to refix. It was a capacitor that was blown out, I think. But the majority reason for X13 failures that I have found is that the return side is a higher static than the supply, and they're pulling water off the coil. I've watched it. If you, and this, of course, this is air handlers with a coil on the return side. And you can take off the doors, put a piece of plexiglass across the air handler, turn it on, and you can watch it with a flashlight. And I've watched water just start. It takes a minute because it's not draining properly. So if it's not draining properly, it starts building up in the pan. Some will be drained out the drain line, but most of it stay in the pan. And it starts getting pulled out of the pan, pulling off the coil. The motor starts getting slowly wet, and then condensation gets in and takes them out. The other thing I've seen is too short of a trap. So on your return side evaporator coils that are on the return side of the air handler, which is the majority of them out there, except for the Hyperion, Train American Standard composite air handlers. The trap's too shallow. It's not draining completely, especially on a high static return, and they're sucking the water out. Remember, you want a deep J trap or an easy trap, but not a run trap and not a P trap. They're too shallow for these motors now. That's the biggest reason I've seen them. And of course, sometimes it is a failed motor just due to the module going bad. And there's ways to tell which is the motor or the module, and we can do a class on that as well. That answer your question?
Yes, thank you, Joey.
No problem. Anybody else?
Okay, well, thank you so much, Joey. Lots of information. I just spent over $17,000 putting a new system in my house without duct work. So after seeing those pictures, I'm going up in my attic and taking a look at my duct work, that new system. Thank you again very much. Thank all of you. Please send us your requests for programs that you would like for us, webinars or training classes that you would like us to do. We're happy to put it together, but we need to know what you need. So if anybody has any questions, you certainly can shoot them to me, shoot them to Joey direct, and we'll see to that they get answered. Don't forget the upcoming webinars that are coming right around the corner. And with that, thank you very much for your support of SCALT. And again, thank you, Joey.
Thanks everybody for coming. I really appreciate it.